All right, so before we start, I wanted to call your attention to Bits and Bytes this week because today there is an involvement fair. There are about 100 or more recognized student organizations, RSOs, that will be holding booths outside of the Nebraska Union from 4 to 6 p.m. And in particular, the UNL Game Development Club will be there with a booth, as well as the UNL Coding Club. So I'd highly encourage you to attend because there are going to be dozens and 100 other clubs that you might be interested in, and it's a good way to get involved. So, this is the only fair that I know of this semester. So make sure to take full advantage of it and learn what opportunities are out there. So just there's a plug again from 4 to 6 p.m. today outside of the Union. All right, so to pick up, excuse me, where we left off last time, I gave you a really, really quick introduction. Here's a Hello World program, and here's how we go ahead and compile it and run it. What I want to do now is I want to go back and revisit that program to explain the actual process that's going on behind the scenes. This is not something that you're going to have to, do yourself at some point, but it's something that you should know is part of the compiling process. Because you jumped immediately from the source code, which would be something like this, to an executable file, which is something that the actual computer can run. There are a whole bunch of other steps in between. In fact, going from source to assembly to machine code, that's a simplified process as it is. What I'm not including here goes way beyond the scope of this course, where there's a preprocessor that goes through and update. We'll talk about that a little bit. Updates your code to do certain things. Then there's an optimizer that optimizes your code to make it more efficient. If there's any dead code or comments, it strips it away. And then finally, you get your machine code down here. I wanted to make that process a little bit more transparent because usually it's opaque. You never see any of these details because you just do gcc hello.c, right? And it produces oops, looks like, where am I? I'm in the right one. What was wrong? Oh, that's right. I never corrected my int. There we go. Thank you. All right, so GCC, and then it produces a hello or a.out file that you then run, right? Well, what I want to do is I want to show you the first step to that of taking this high-level C code here and producing what's called assembly code. So I'm going to go ahead and tell GCC to only make the assembly code here. Hello.c, right? And when it does that, again, no news is good news. When it does that, it produces this hello.s file, right? Which is what assembly looks like, right? It's not very human readable. It's not very friendly at all. But if you eventually take a systems course, you will be writing assembly that looks something like this, where you're moving the contents of a memory address into a register, or move the contents in this register 5 to register 6, something like that, right? Now, there is some parts that are human readable. For example, where's my string hello world? Yeah, there it is. There's the string hello world, right? And there's also like an external call here. We're calling a method called puts. That's how printf actually works. It calls this other method that's responsible for everything. But otherwise, it's not very human readable at all. Now what I'm going to do is I'm going to do that last step. I'm going to take the assembly and turn it into machine code. GCC-O. O says produce an object file, which is just going to be a binary object. Hello.c, right? Oops. Sorry. C. I made that same mistake this morning. C stands for compile, but do not produce an executable. Now, when I list all the files again, I see this hello.o file. I'm going to go ahead and refresh over here, and I'll see it now. I'm going to try to open that up. And the editor says, you can't open that up because it's just a bunch of binary code. It's not plain text code. It's not human readable. It's not intended for a human. It is intended for the machine, right? It is intended for the actual metal processor, so we can't look at it. Yeah, go ahead.
Is it like really, really long? Is it just ones and zeros?
Yeah, in fact, we can look at it being ones and zeros using hex dump, right? Hex dump, the canonical form here, and then hello.o, right? There's what it looks like, right? Now over here, it's trying to interpret, in this column over here, it's trying to interpret it. And some things are interpretable. For example, if I jump up all the way to the top here, where's my hello world? Somewhere it's in there. The string, I'm missing it. I'm going too fast maybe. Where is it? Oh, there it is. Hello world. There's my string that I'm trying to produce here. So that ends up being interpretable and printable. But all these dots, it's just a bunch of machine code. It's a bunch of raw data over here in hexadecimal. Hexadecimal is base 16. We are humans. We count base 10, 0 through 9. Computers count in binary, zeros and ones. Another way of representing that is through hexadecimal, which is 0 through 9 plus A through F. Right? It gives you 16 characters to work with instead of 10 characters or 2 characters. It's a more compact way of writing binary code right there. Right? So do you ever have to actually write binary code? No, that's how computing started, though. Back in the 50s, 60s, whenever, right? They actually had to program a computer by doing a bunch of punch cards. Programming in binary. 0, you punched it and it was a 0. You left it alone, it was a 1 or something like that, right? Then along came assembly, which abstracted that away a little bit and allowed us to have commands that the processor would understand. Still not very human friendly here at all, right? Nobody is going to read this off the top of their head unless they are embedded systems people that only write in assembly. So that's where languages like C came along, right? It was another abstraction layer on top of that. In other words, we're down at the machine level here, which we don't understand. Then we've got an intermediate, and then finally we've got a higher level programming language, which is not complete English yet, but it is way more readable. You could probably understand what this does or have an intuitive notion of what this does just by reading it out. Right? For example, here's another program. If I just opened up this program, all right, let's ignore the, of course you can know what it is immediately by reading the documentation. But if we just walk through this, I've got miles and KMS, that's probably kilometers, right? And then please enter miles, we prompt them for input. And then we scan, probably scanning the input. And then we produce this value here, kilometers per miles times miles is equal to the kilometers. And then we output it down here. So we could probably have an intuitive notion of this is probably converting miles to kilometers, just like it says up in the documentation, right? But we would never get that from something as low level as just plain old binary or even assembly code here. When you go to GCC it, like we've done before, you're going from source code immediately to machine code. It's doing all that stuff in the background, converting it to assembly and then converting it to machine code and linking stuff in and doing a bunch of 50 other things, but you never see that because the magic of the compiler. Yeah?
When you did that kilometers to miles program, I don't think it ever said in the multiply something by 1.6 and 1944.
Yeah, so we'll get to that. It's right here, right? That 1.6 kilometers in a mile. We multiply whatever miles you want to convert, and then we output the kilometers. That's what we're doing right there. But let's talk about the anatomy of that program, okay? The first thing that you see at the very top, though, right, let's go ahead and start at the top. What's the first thing you see? Documentation, right? This is done through comments. So what are comments? Comments are human-readable messages embedded in code, right? They are ultimately ignored by the compiler. One of the things that the compiler does is goes through and looks at all of your comments, immediately throws them out because they never end up in the actual program, right? They are intended not for the machine, but for other humans, for yourself even. If you come back 3 months from now from code that you wrote, what was I thinking when I wrote that, right? Documentation helps with that. The syntax is pretty straightforward. There are 3 ways of doing this, actually 2 ways, but there's a third way that we'll talk about here. A single line comment. If you jump down here, we put in a single line comment prompt for the user, right? It's green, so you know that it's a comment, it's ignored. Right? Anything after that, / or \, which ones are those? Those are forward slashes, right? Anything after the / is completely ignored until you get down to the next line. Then it matters, right? It's no longer green, right? So undo, undo, undo. Multi-line comments begin with a /* and end with a */. So I could have done something like this. These are the variables that I need for this program. And you see that it goes on 3 different lines, actually 5 technically, right? But that's a multi-line comment. Slash star and then star slash. This is a terrible comment. We'll talk about good comments here in a second, but I'm going to go ahead and get rid of that. Right? All comments are ignored by the compiler, the system, etc. Now there's a third one that we've used for the author header there called doc-style comments. They are simply just multi-line comments, but they begin with a slash star star by convention, right? And a vertical line of stars to offset them. Again, the reason that you would want to do this is so that you have this nicely ASCII formatted, this ASCII art, basically, formatted documentation. For now, the only documentation we're expecting from you in the first few weeks is an author documentation. Who wrote this program? What is the purpose of this program? When was this program written? Right? Basically, if you're writing an English paper, you'd do the same thing. You'd put your name, date, class, whatever, right? We know what class you're in. So we're only expecting author, date, and purpose of the program for now. Right? But otherwise, you see the star star there. If I didn't have that star star, it would still be green, but it would not be a doc star style comment. Right? You can get into the habit of writing these things by simply just going slash star star and then hit enter. It does autocomplete for you. So enter, enter, enter. It'll keep the vertical stars aligned for you. Get into the habit of using them because this convention is used in nearly every programming language. Java, C, C++, C#, PHP, JavaScript. The one exception there is a Python because Python does comments differently. They're hashes instead of slashes. Right? All right, so that's our first item. Again, what is the purpose? It's to communicate intent to other human beings. What is the purpose or intent that your code had, right? Comments and documentation should tell you the what and the why, right? What does this code do? Oh, it converts miles to kilometers. Why does it do it? Well, it's because we needed a program to do that, I guess, right? It's not necessarily the how. The code is the how. How does it successfully read in from the input from the user? How does it do its math? And how does it do its output, right? Once you are familiar with that, it's going to be self-documenting. For example, once we've learned about printf, right, we'll know that this prints please enter miles into the standard output. Right? In fact, let's go ahead and take a look at it in action so that we understand what's going on here. Mile converter, GCC mile converter. That produces a.out. Right? It's now prompting me to enter in a bunch of miles. Let's go ahead and enter in 10 miles. That's going to be about 16 kilometers. When I hit enter, it outputs, just like down here, 10 miles is equal to 16 point some kilometers, right? Now, how did it do that? Well, first of all, it prompted the user for the input. It read the input from the user. Then it did a calculation here. Then it did another print, right? Now, once you are familiar with these things, say in a couple of weeks, right, or even after a couple, like 1 week or 2 weeks, you don't need that kind of documentation that I just erased, right? This is for demonstration purposes, so that you know what this line does. If you are already familiar with printf, you know what it does. The code is self-documenting, right? And once you're done with the entire semester, you will understand almost every single line of code that C has, and you will not need to document every single line. That's called cruft, right? Don't leave cruft in your program, right? At the very beginning, of course, if you want to document every single line, go ahead. We're going to discourage that as we go along and then start taking points away from it as we go along. But not every line needs to be documented like this. This would be sufficient for anybody that knows C. But I'll leave those in there because I wanted to have them as examples of single line comments. Yeah? Cruft, yes, good. C-R-U-F-T. So that term it's some jargon. It comes from Harvard or Yale or somewhere where there was a building called Cruft Hall, right? And it was disused. Nobody actually used it for anything. And so what happens when you've got like a broken table or you've got broken chairs or you want to get rid of stuff like old overhead projector because we've got new technology, you threw it in Cruft Hall. Eventually, Cruft Hall filled up with garbage, right? That's why we refer to it as garbage in the code. It's clutter. Get rid of it. Garbage should be thrown away properly or recycled. Right? Okay? So get rid of the cruft. Right? Again, for now, all we're looking for is that you should have an author which name or names if you're teaming up with somebody, the date, maybe your email, the purpose of the program. Name and purpose of the program are the bare minimum. Okay? Again, it should not be cruft, right? Cruft is unneeded clutter that's in your code that should not be there. Right? It's just distracting. If you have a lot of distractor code in your code, then it's really, really hard to read what it's doing. Okay? Instead, code should be self-documenting. The code itself should tell you the how. Right? Write good code to begin with. All right. That was our first thing. There's comments. What's the next thing? These are called preprocessor directives. And what do we talk about with the std-lib, which stands for standard library, and std-io, so standard again. IO is going to be input output. So we're bringing in a bunch of libraries. We've got this hash and then include. We also have a very similar one down here, hash and then define. Both of those are what are called preprocessor directives. And preprocessor directives always begin with a hash, right? You can include external libraries using include, right? Plus the name, and provide the name of the library. Generally, this is going to be a header file, and so it's going to look like we just did with stdio.h or stdlib.h, right? That's a header file. We'll talk about header files in detail when we start to write our own header files, right? Here's some examples. Again, would be the standard library and the standard IO library. Another excellent example is going to be math.h. What kind of functions do you think are in that library? Math functions, right? It does what it says on the tin. For example, sine, cosine, or SQRT. What do you think that's short for? Square root, right? Everything that you would see on your typical calculator. No, you don't have to write your own. You might eventually want to write your own. In fact, you probably know how to do it if you're taking Calc 1 or 2, right? How would you compute sine using your Calc 1 knowledge? There's a Calc 2? A series, yes, exactly. A Taylor series approximation, right? Those are terrible, actually, for approximating sine and other functions. There are much better methods of doing so. But what about that square root? Is there a Taylor series for square root? It's been so long, I don't think there is, but there might be. In any case, who cares, right? It does. I mean, do you ever wonder how that square root button works on your calculator? No, who cares? It just works, right? You can go ahead and use those if you bring in the math library, right? Yeah. Yeah, there are logs too. There's log, which is log base E. That's the natural log, I think, right? And then there's a couple of other. You could use your rubber duck debugger over here to tell me what functions are available in the math library. Hopefully it can do that. What functions are available in math.h? Right? Probably not going to give you an exhaustive list, but has a variety. Square root pow for raising x to the y, log for the natural log, x e to the x, right? And sine, cosine, and tangent. Yeah.
So when you use the include or the math hashtags, those bring in functions that you can use.
Exactly.
But what the define seems to work different.
Yep. So let's go ahead and talk about that now. But before we do that, let me mention one more thing about the math library. It also has these constants, right? So if you need a pi, it's m_pi in the math library. If you need e, it's m_e. And that is achieved through, as you already observed, the define macro. All right, that's called a macro. It's essentially a cut and paste operation by the preprocessor. So let's go ahead and look at the define. Define kms per mile to be 1.60934, right? Now what the preprocessor does is it goes through your program, and anytime that it sees kms per mile, like it does right here, does a cut and replace. So it cuts that and replaces it with that actual number, right? What if we didn't have this? Did anybody know, without being reminded, that there were 1.6 kilometers in a mile? Maybe you did. Those are called magic numbers, right? What if I said, oh, it was 2.71? What is 2.71? That's E. Okay, you knew that. But what if I did like 1.73? I don't even know if this is correct or not, but we'll have to look it up and see if I'm right. If I'm wrong, maybe it's not jogging your memory. But the golden ratio value? Right. What's the golden ratio? Oh, 1.61. That's it. All right. There we go. There. If I just had that random number in there, would you know what the hell that is? Right? No. So what we do instead is we use preprocessor directives, giving it a human readable name, kilometers per mile, right? And then I don't have to have a bunch of these magic numbers in everywhere. Not only that, but the added benefit is if I wanted this to be more accurate, I change it in one place instead of the 50 places that I've used it. Yeah.
So what's the difference between like using the define and then when you go down, you have KMS equals the two numbers multiplied?
So this is basically a constant, right? It will only ever be a number, not a variable. We'll get to these eventually here. These are variables. They can vary. I could have a value of 5, or I could reset it to 7, or 8, or 10, right? This will only ever have one value. I could reset it, but then I would have to recompile it. In the program itself, it's only ever going to have that one value, right? Constant, right? That's the opposite of a variable, right? It's just a constant. Okay. All right. So again, macros allow you to define constants, a single value to represent a single place, in a single place. In other words, constants. Macros make your code more readable and maintainable because you're not using these magic numbers. We call them magic numbers because you ask, where did they come from? I don't know, magic, right? What is this number? 61, the golden ratio, right? Or 0.12345678910111213. That's the Champernowne constant that we should all know, right? No, right? It's just a magic number. Don't use magic numbers. Give it a name, right? Give it a proper name. Okay. What comes after are preprocessor directives. And by the way, this is also a cut and replace. All it's doing is going out to this file on the system, taking the contents of that file, and then putting it right there instead of the include. Right? That's how it ends up importing a library. It just does a cut and paste, just like this is a cut and paste. And that's the preprocessor. What comes next is the main. Every program has to have a starting point. And in all programming languages, that's going to be the main function or the main method. Okay? And in C, that's the main function. Right? So again, every program has to have a starting point, and for us, that's going to be main. After that, what's called linear control flow takes over. A program will always execute top to bottom, left to right, unless it's interrupted by either a conditional, which we'll talk about after the basics, or a loop, in which case it repeats this code over and over. Right? Otherwise, it goes and executes line 14. Then it executes line 17. Then it executes line 20, then line 22, etc. Top to bottom, left to right. Okay? That's linear control flow or sequential computing. What else do we see? And I'll ask you now. What other things do you observe? Let's start again at the top here. On line 12, besides the main, what else is there? What about that guy right there? Opening parenthesis and closing parenthesis. Those are like functions, right? If I were to write a math function, f of x is equal to x squared, right? Something like that. It's the exact same thing. F is the name of the function, and it's not too descriptive because all functions are named f or g or h in math, right? Well, what if it was a sign instead, all right? So f is equal to sine of x, right? What is x in this case? The variable or the input to the function, because it produces output. Y is equal to x squared, right? So we have the same thing here. If we've got a function, we've got parentheses, and then those are the inputs. This is an input, and this is an input. What's int? What's char? What are these stars here? Don't worry about it. We'll do that later, all right? So immediately I see things like punctuation, right? Punctuation. For example, parentheses define function inputs, which are arguments or parameters. Right? Those are other names for them. You'll see them. Arguments and parameters Just think of them all as inputs to the function. We do the same thing down here. You want to print something. There's this function that will print something. So what we'll do is we'll put whatever we want to print inside of those parentheses. That's our input to the function. Right? There is no output of this function, otherwise we would be capturing it. Right? We'll talk about that later. What other punctuation do you see? Well, again, let's just go in order here. What about this guy? Opening curly bracket and a closing curly bracket. Right? It's kind of like our paragraph. Right? Opening curly brackets, closing curly brackets denote blocks of code. Right? So let's go back over here. Opening, closing curly brackets. In other words, these things, ... denote code blocks. Code blocks. Right? Similar to paragraphs. Right? In English. I don't know why I quoted that, but whatever. Right? All right, so in English, how do you know that a paragraph begins and it ends? What do you do at the start of a paragraph to say that a new idea is being formed here? Indentation, right? And then the next paragraph is indented, right? Et cetera, et cetera. How do we do that in code? We have an opening curly bracket and a closing curly bracket. This paragraph, or we call them code blocks, is inside the main. That's the main code, right? There might be things outside, right, that we could put, but we're not doing that yet. But they're not a part of the main. They're not a part of that paragraph, that code block. All right? All right, what else do you see? Here's the next line here. What's within that line, first of all? A comma. I'm creating variables here. We'll talk about that in a moment. But what about the punctuation here? What if I didn't have that punctuation? Right? That's not a list, right? If I say I want candy, or I like ice cream and cake and candy, right? If I were to write that in English, what would I be separating those things with? Commas. So commas separate lists, right? Commas denote items in a list, right? We don't have lists in C, so if you're familiar with lists, say in like Python, it's not the same thing. I'm just saying that there are commas that denote lists, separate things in lists. Right? What was at the end of that line, by the way? A semicolon, right? So semicolons are kind of like what in English? Exactly. Semicolons end each executable statement, right? Like a period in English. Right? This is why we read, again, why is linear control flow the way it is? Why is it read top to bottom, left to right? That's how we read English, right? We're trying to make programs that look kind of like English, which is why we adopt all these conventions when we create programming languages, right? All right, well, you might eventually see, or you will eventually see square brackets. Those are denoting arrays, which we'll talk about much later, okay? But I don't have an example right now. What about double quotes? Double quotes denote what are called strings, right? That is sequences of characters. For now, what do we have? Well, we just have this string, please enter miles, just like we had hello world before. We also have this string, which has these other strange characters in it. We also have special control characters like this. What backslash, right? What did the backslash n do? It goes down to the next line. Well, what if I wanted to print a tab? Right? Can I just tab over? Right. Nope. The way that would insert a bunch of white space, yes. But if I wanted to do a tab, it would be \t, because if I just hit the tab key, that would actually change the source code, not direct the source code to print a particular character. There are a couple of others, but for now, all you need is the end-line character, /n, or \n, and then \t if you ever want a tab. Okay? All right. What else is there? Let's see. Likewise, single quotes can denote single characters. So, for example, if I wanted a capital C, just one character, not a sequence of characters, but just one character, I would use single quotes. Single quotes for single characters, double quotes for multiple characters. Really easy to remember. Capital C and lowercase c are not the same thing, because everything worthwhile in computer science is case sensitive, right? If you named a file mileconverter.c, and then rename the file with a capital M, capital C, capital T for whatever reason, that's not the same file. They're completely different files. Everything worthwhile, everything that matters is case sensitive in computer science. Right? All right, some other things that we'll get to here in a second, but as far as punctuation goes, or grammatical things, what do you see here that is the absence of something? In other words, nothing or white space can also be useful here. Right? What have I done with everything inside of the main? I've indented it. Why would we do that? Think about English again. If you've got a bullet pointed list or an outline, idea A, B, C, right? Now, sub idea A1, what did you do? You tabbed over, you indented. Another idea, a sub idea to that, you would indent over. You don't want too much indentation, maybe 2 or 3 levels at most, but otherwise you keep everything at the same indentation level because the white space makes it more readable that way. Right? I also added in vertical white space. That's not necessary. That's not absolutely necessary. For example, I could go ahead and get rid of that vertical white space because these 3 lines kind of belong together. I'm going to group them together. It's kind of like a paragraph within a paragraph, right? Multi-sentence paragraph or something, right? Do not just blindly double space everything, right? Like you would an English paper because you have to hit that 5-page limit, right? So double spacing it, now I only have to write 2.5 pages, right? Or do 1.5 spacing, and now I only have to write 2 pages, right? Now, we're not assessing you by the page here, right? In fact, shorter code is generally better, right? So you should make it look nice. If this looks nice, yeah, great. If this looks better, yeah, okay, fine, right? It's a judgment call. It's what we call it the Goldilocks zone, right? Not too hot, not too cold, just right. I can't tell you exactly what's just right. I can just look at it and say, no, that's ugly. Or I can look at it and say, yeah, that's beautiful, right? That's just right, okay? So vertical and horizontal white space are also tools of style in your programs. Code at the same level, at the same block should be indented and indented at the same level. It should all be aligned like this is, right? I shouldn't have this where, oh, I forgot to indent that one. I indented this one by tabbing over 3 times instead of whatever. This one, instead of tabbing over, I'll go 2 spaces instead. Completely inconsistent. Vertical white space can be used to chunk pieces together for the same code block, right? That these kind of belong together. I'll go ahead and chunk them, right? What are we going to be grading on? We're going to be grading on consistency, right? This is not consistent at all, right? How do I recover from this? Well, first of all, get into the habit of writing good code to begin with. But if you ever need to recover from it, you can use something called A-style, right? A-style mileconverter.c. All right, there we go. And I have to close it and open it back up to show you that it fixed all my idiotic spacing, right, for me. A-style will automatically style it for you. Now, it won't solve all of your problems with style, but it will take care of most white space stuff. Right? Online C formatter. Right? I forget which one this is. Let's check it out. No, not this one. There we go. There are lots of different, yeah, go ahead.
Are specific indentations ever required for the code to actually function properly?
No. For functionality, white space doesn't matter. You can get rid of every single piece of white space except for, like, say, that white space matters. Please enter. There's got to be a space in between there. But I could take, and it's called minifying. Get rid of that. I could put everything onto one giant line if I really wanted to. There we go. Right? Not readable at all, but the compiler doesn't care. Right? It's going to compile just fine. Right? In fact, let's go ahead and compile just fine. Let's make sure that A-style fixes our mistakes. And there we go. It fixed it. But it didn't put those vertical white space in there. Yeah?
Yeah.
Yep, and get rid of that space. That space, you can get rid of that space, you can get rid of that space, you can get rid of that space. You cannot get rid of that space because now the name of the function is int main, right? So some of it is, you can't get rid of this either, sorry. But you can get rid of that one, right? And let's style this again, see if it fixes that. Okay, good. Oh, it didn't fix all my white space. That should be in there, but there we go. Right. It did at least take that down to the next line. So now, are there rules for this? Yeah, if you work at Google, you're going to use the Google style guide. If you work Mozilla, maybe is no, Chromium is also Google, right? Yeah. Mozilla is a different organization. GNU is a different organization, right? LLVM, that's a different organization. These are all just different style guides. But if you were to take this and put it over here, it's going to look completely different if you were to write this at Google, maybe. Looks like we're conforming to Google. Let's go ahead and go with GNU instead. There we go. Did you see what the difference there is? GNU folks like to have int and then take that name down to the next line. They really like copious amounts of spaces everywhere. That opening curly bracket is now on its own line, right? So it doesn't matter as long as you're consistent about it. I'm going to show you a generic style. I'll always use this style, which is kind of like Google style, right? It doesn't matter because you work at a place, they're going to have their own style guide, and you'd have to conform to that. And usually they'll have a tool anyway, like a style, that will, however you write it, it's going to restyle it before you check it in, right? Just get in the habit of writing consistently, right? That's what we're going to be grading on. If you indent 5 spaces here, 3 spaces there, 7 spaces there, that's going to be points off for style, right? Okay. All right. Now we can go back to the very top of the program and talk about that double miles and KMS. These are called variables. They're called variables because the value stored in those variables can vary. It can be 5, or it can be 4, or it can be 10, right? It's not going to be constant. C is what is called a statically typed language. Now, what does that mean? It simply means that you have to declare a variable before you can use it, right? You have to specify the name, the name, that is the identifier, and I'll put this other one first here. You have to specify the type, right? Say an int or a double or a char, right? We'll talk about all 3 of those here in a second. You have to do that before you actually use your variables. For example, if I move that declaration down here, right? I'm trying to use miles and kilometers before I've declared them. GCC, the compiler, will not allow me to do this. It'll come back with a message saying miles is undeclared, right? It reads top to bottom, left to right. When it gets to this first instance of miles, have you seen a variable called miles yet? Nope. So it dies, right? It can't see this, and so it has to be declared beforehand. You have to declare them. There's the type. There are the names. If you've got multiple variables, of course, of the same type, you can use comma to separate them. If I wanted an integer variable, int, number of students is equal to 100 in this course, right? I could do something like that as well, right? I'm only initializing it right here, right, to 100. Later on, I can change it. Number of students, say we get 10 more enrolled. I'll go ahead and change that to 110, right? We'll talk about the assignment operator here momentarily, but let's talk about each one of those types, right? The first one, int, what do you think that stands for? Integer, right? It's short for integer, a whole number, negative, positive, and 0, right? However, it's only, there are only 32 bits in an integer, right? Now, what does that mean? It has a limitation. Int is a here's the technicality here. I'll replace it with the technicality. It's a 32-bit signed 2's complement integer that can represent whole values in the following range, right? And here's why it's in the following range. Negative, that's 2.147 billion negative, and then 648, and then positive 2.147 billion, and then 47. Why is that? Well, if you've only got 32 bits, that is zeros and ones, you can only represent so much. For example, base 10, if I only gave you 3 placeholders, what's the maximum value that you could represent? 999, right? If I gave you 4, you could represent something a little bit larger. If I gave you less, only 2, at most you could represent 99, right? So if you, integers are infinite. If you look at the number line and go negative and go positive, it never ends. There is always a smaller integer, there's always a larger integer. But computers are not finite, right? You know this very well because you eventually run out of memory. Or, that AAA game won't play anymore because it requires 128 gigabytes of memory, right? And no matter how much you put into your computer, it will still be finite. There will be a limit. Our limit for integers here is going to be about 2.147 billion and negative 2.147 billion. Why is it 47 versus 48? Well, you got to represent 0, so you got to take it from the other side. You also can only represent up to these numbers are 2 to the 31st and 2 to the 31st minus 1. Where's that missing bit? That missing bit is positive or negative. So you need a sign bit, and then the remaining 31 bits can be used to represent the number. Right? Question? Nope. Okay. All right. All right. Well, what about a double? And why is it called a double? All right. Here's the technicality. Yeah. Here we go. It's an IEEE 754 floating point number. Right? Don't worry about that. It's a fractional number. 3.5, 10.0. Even if there's no fractional value there, 10.0 is still a floating point number. Negative 3.1415, whatever, right? And 0.0, right? Those are floating point numbers. In other words, decimals or fractions, right? So decimal numbers, right? It's a double because it is 64 bits, right? However, there's still a limitation here. We won't go into the limitations in detail. Just know that you can represent any fractional number, but only with at most 17 digits of accuracy. Right? So there's still a limit, right? Even though it's double the size, 64 bits, and it's a floating point number, so it has a fractional value, you still have a limit on the amount of information that you can represent. For example, let me go ahead and go back to the Hello World program over here. All right? Now let's create some variables. Int. Let's see. I want that number. Where's that number? There we go. All right. So int x is equal to, that's the maximum value, max value. Right? Double y is equal to 3.14159, and then I'm just going to mash my keyboard here. That's more than 17 digits, right? Is it going to be able to hold that information? Let's find out. Let me print them out. X is equal to %d is a placeholder that we'll talk about later, and y is equal to %f, that's another placeholder. I'm just going to print out the values of x and y. Right? And let's go ahead and gcc hello.c. Right? Printf, sorry. All right, and let's go ahead and run that. Right? All right, well, it was perfectly fine with that number, but that's the maximum value that we can represent. What about this one? Well, it only prints out to 6 decimal places by default. I can change that by printing out to 100 decimal places. Right? Let me go ahead and show you what that looks like. There we go. There's a big number. First of all, what happens when you get low enough? It doesn't have any information. But also, what happens with the original number that I put in? So on top, that's the original number. That's what it printed. Right? It's accurate to there, the same, and then finally right there. Those two are not the same. It's 3 up here and 5 down here. In other words, only these digits were accurate. How many digits do you think they're there? 17. Right? Once you get past 17 digits, it's just garbage. It's I'm just guessing. Right? It's flipping a coin, basically. Right? All right. What happens when you try to exceed these values? So let me go ahead and set x is equal to x plus 1. All I'm doing is adding 1 to it. It should be 2.147 billion, blah, 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 48, right? Let's find out and print it again. What happened to it? it became negative. A positive plus 1 becomes negative. Not in math world, but over here in computer world it does. This is because in math world, the number line is an infinite line. From your perspective, positives go that way, negatives go that way. It's not like that in computers. Computers, it's finite, so it's a circle. What happens when you go positive, 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 positive? You end up going back around to the negatives, right? So you've got your number line here, wrap it around so that it forms a circle. That's called overflow. And if you try to represent a number that's larger than this value right here, then it's just going to wrap around to a negative. It's called overflow or underflow. And you'll see that in your lab next week. Right? What happens when you do need to represent numbers that are larger than this or more accurate than this? Then you need to bring in a library to do it. Right? Or use a long as a double integer, which is 64-bit integer. There are 128-bit integers, but beyond that, now you're talking about doing everything in software, which is extremely costly, which is computationally, and it's no longer efficient. Right? This is pretty much good enough for like 99% of the use cases that you'll ever have, especially for this class. Right? All right. What about that last one that I kind of mentioned? We'll mention this, and then we'll look at the table. Char is a single ASCII character, short for character. Right? Here's the ASCII text table. Let me go ahead and open. Okay, it doesn't open links over there, so I'll go ahead and go and copy and paste. So this actually predates modern computing, I think. In fact, this was done in the, Roosevelt, I think it was in the Truman administration in like the 50s. All these characters were set down. For example, capital A through capital Z. Those are self-explanatory, as are lowercase a and through lowercase z. Each one of these is given a decimal number. For example, capital A is assigned the decimal number 65. Lowercase n is given the decimal number 110. Right? There are a bunch of other control characters here. For example, where's the n-line character? It should be like 32, right? No, 32 is space. Where's the n-line character? 10? Yeah, there we go. If you, that / n, that also has a character value of 10. Right? There are some things that if you tried to print them, for example, character 7, that's a bell, right? There's also a line feed versus a vertical tab versus, what's the other, horizontal, backspace, acknowledge. There's another one, I forget what it's called though. There should be a line feed here somewhere. Line feed, new line, form feed, new page. It should be like /r, but I'm not seeing it right now. Why do we have all these? Why do we have a bell? Why do we have a line feed? Why do we have all this stuff? What did we type on before computers came along? Typewriters, right? What happens when you're on a typewriter when you get to the end of the line? Ding, bell. What do you need to do? You need zip. That's a line feed. It not only goes back to the first column, but then it also line feeds down to the next line, right? So those are two operations: the zip back and then going to the next line. Right? These are all legacies of the technology that preceded modern technology that are still in use today. Now, we do not use just the ASCII text character set anymore. Instead, we use something called Unicode. Unicode smiley, right? So that you can have your nice little full emoji list, Unicode, right? You can also have CJK fonts, Chinese, Japanese, Korean fonts. You even have ancient hieroglyphics supported, or things like this. Now, this also has a number. If you zoom in on this, what is the number? Well, it's much larger. 1F600 for this smiley right here, right? And I believe that you can do something like this, but you shouldn't, right? There we go. Can I write a program to print a smiley? Yes, I can. Don't do that on the grader, though. Can I even have a variable using a smiley? I believe you can, but don't do that. Terrible, right? But it's just another character, right? But we're going to stick with the ASCII text table here in this class. Right? I'll see you on Friday. And remember the involvement fair today.